J.J. Thomson. In 1897, J.J. Thomson's groundbreaking discovery of the electron dramatically altered our understanding of the atom and laid the groundwork for modern atomic physics. Before Thomson's work, atoms were thought to be indivisible units of matter, the fundamental building blocks of the universe. This was what Dalton's atomic theory suggested at the beginning of the 1800s. But the way they pictured it was nothing like the picture here, not yet. Dalton had been able to explain the way substances react with each other by way of a theory that everything breaks down into fundamental, indivisible elements or uncuttables, which is the meaning of the word atom. However, Thomson's experiments suggested there were even smaller particles within atoms. He passed an electric current through a gas under certain conditions, and the result was a glowing stream of what he called cathode rays. When he then subjected them to electric and magnetic fields, these rays were deflected, indicating that they were composed of negatively charged particles. He later named these particles electrons. He discovered that these negatively charged particles were much lighter than atoms. This fact suggested that atoms were not indivisible, but composed of smaller entities, although how he pictured them was not yet anything like the picture here. The discovery effectively ended the reign of Dalton's indivisible atom and marked the beginning of subatomic physics. As a result, Thomson proposed a plum pudding model to describe the atom's structure. He likened it to a sphere of positive charge in which electrons were embedded, like plums in a British pudding. While this model would soon be superseded, Thomson's work opened the door to a more complex and nuanced understanding of the atom. He set the stage for the scientific inquiries that led to the development of quantum mechanics and the Standard Model of particle physics, frameworks that are fundamental to our current understanding of matter and the universe. About 10 years after Thomson's discovery of the electron, Ernst Rutherford took the discussion a step further. Thomson's plum pudding model proposed that electrons were scattered within a diffuse cloud of positive charge. In 1909, Rutherford decided to probe the atom's internal structure further. The result was the famous gold foil experiment. No, not what's pictured here. Rutherford and his assistants took what were called alpha particles, positively charged, and directed them at an ultra-thin gold foil. According to the plum pudding model, these alpha particles should have passed through the foil with only slight deflections due to the dispersed positive charge. To Rutherford's astonishment, while most alpha particles did go straight through, some were deflected at large angles. A few even bounced straight back. This observation led Rutherford to a groundbreaking conclusion. Apparently, most of the atom is empty space, unlike Thomson's proposal. The positive charge in an atom must be concentrated. Rutherford proposed in the middle in a nucleus, like a human cell. He proposed something like a solar system model of the atom, with electrons orbiting the nucleus much like planets around the sun, but with vast empty spaces in between. This nuclear model of the atom was a dramatic departure from the plum pudding model. It suggested that atoms, rather than being diffuse clouds of charge, had a compact nucleus at their heart. Because this approach opened the way to the modern understanding of the atom, Rutherford is sometimes referred to as the father of nuclear physics. He set the stage for the quantum insights to the atom that would quickly follow.